NASA's Galileo spacecraft reached Jupiter with its main high-gain antenna still folded like a jammed umbrella. That 4.8-meter dish was supposed to carry large amounts of science data across hundreds of millions of kilometers. Engineers tried to free it and failed. The mission continued through two small low-gain antennas that were designed for much slower communication. Galileo therefore faced an odd rescue. The spacecraft could still see Jupiter, but Earth could not receive the planned flood of pictures and measurements. The team had to shrink, sort, store, and transmit the science differently. This episode asks how a mission built around one large antenna recovered most of its objectives after that antenna never became usable. Galileo launched in 1989 and traveled through a route that included Venus and Earth flybys. During the hotter inner part of that journey, the umbrella-like high-gain antenna stayed furled behind a sunshade. Controllers used low-gain antennas for cruise communication. The large dish was scheduled to open in April 1991 after the spacecraft had moved far enough from the Sun. A motor drove the deployment, and 18 ribs were supposed to spread a metal mesh reflector into shape. Telemetry showed that the motor stalled before the antenna fully opened. Tests and analysis pointed to a few ribs, probably 3, stuck against the central tower by friction. The spacecraft now carried a large reflector that was almost open and completely useless for its intended high-rate link. The flight team explored ways to release the stuck ribs without damaging the spacecraft. Controllers cycled the deployment motor many times. They changed the antenna's temperature by turning Galileo toward and away from the Sun, hoping expansion or contraction would loosen the pins. They spun the spacecraft at different rates and used maneuvers to add small forces. Ground teams tested spare hardware to understand which ribs might be stuck and what loads the antenna could tolerate. None of those attempts completed the deployment. The team eventually had to stop treating the dish as a recoverable device. Continuing aggressive attempts could consume time, fuel, or hardware margin while Jupiter approached. That decision created the mission's real engineering problem: make the low-gain system do work it was never expected to carry from Jupiter. A low-gain antenna spreads radio energy broadly, which makes it forgiving about pointing but weak over long distances. Galileo's planned high-gain dish would have concentrated the signal toward Earth and supported much higher data rates. The small antennas could not simply send the original stream more slowly without consequences. Jupiter encounters generate time-sensitive observations. Images, fields, particles, and atmospheric measurements compete for limited memory and transmission time. Galileo also needed to receive commands and report engineering health. Engineers therefore treated communication as a complete system rather than one broken part. They examined what the spacecraft could process before transmission, what its tape recorder could hold, how the deep space network could hear weaker signals, and which observations mattered most during each encounter. New flight software gave Galileo more work to do onboard. The spacecraft could compress images and other data before sending them. Lossless methods preserved every value where precision mattered. Lossy image compression could discard some detail when a smaller file was more valuable than a perfect but undeliverable one. Engineers also changed image-taking plans, using smaller areas, fewer frames, or different compression settings for particular targets. The tape recorder became a buffer. Galileo could gather data during a close flyby, store it, and play it back across the quieter weeks that followed. This turned a brief encounter into a long communication schedule. The spacecraft was no longer a camera feeding a live high-rate link. It became an editor with a very slow mail route. Engineers improved the Earth end of the link as well. NASA combined antennas in the deep space network so several dishes could listen together. Receivers and signal processing techniques extracted useful data from the weak transmission. Ground changes and onboard compression raised the effective return far above the bleak early estimates, even though they never recreated the original high-gain capacity. Mission planners scheduled playback around geometry, antenna availability, and scientific priority. A dramatic image of Jupiter could take many decisions and a long stretch of downlink time to arrive. The rescue, therefore, did not happen in one command. It lived in years of software, network upgrades, observation planning, and patient playback. The large dish remained visibly stuck, while the invisible communication system around it kept improving. Galileo entered orbit around Jupiter in 1995. It sent a probe into the planet's atmosphere, observed volcanic activity on Io, studied Europa's surface and possible subsurface ocean, and watched the Jovian system through repeated moon encounters. The antenna failure reduced the amount of data and forced hard choices, but it did not reduce the mission to a token demonstration. NASA reports that the great majority of original objectives were met, while new objectives were added. That outcome does not mean the antenna was unnecessary. Every compressed file and skipped observation reminds us what the mission lost. It means the team found enough value inside a much smaller channel to keep the central exploration alive. Galileo explored Jupiter after its main antenna failed by changing the mission around the antennas that still worked. Engineers stopped trying to force the jammed dish, rewrote flight software, compressed data onboard, used the tape recorder to stretch each encounter across weeks of playback, and strengthened the deep space network on Earth. The rescue never made the low-gain link equal to the original design. It made limited communication useful enough. That is why Galileo's story feels different from a repaired part. The hardware failure stayed in place for the rest of the mission. The fix was a new relationship among spacecraft software, ground antennas, scientific priorities, and time. The mission also changed how scientists thought about a picture before taking it. A frame now had a visible cost in recorder space and downlink time. Teams chose which moon, filter, resolution, and compression level could answer the strongest question. Some data traveled in full detail, some arrived as compressed summaries, some observations never fit the budget. That editorial discipline was not a substitute for bandwidth, but it prevented the weak link from filling with low-value material. Galileo's rescue joined engineering and science planning so closely that the choice of one image began long before the camera opened. The long playback schedule changed the audience's sense of an encounter too. Galileo could pass a moon in hours and spend weeks returning what it had recorded. A close approach was no longer a burst of immediate pictures. It became a queue of measurements arriving through a narrow door. That slower rhythm rewarded a system built to remember, compress, and prioritize. The stuck dish turned time into part of the communications hardware.